NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math lesson on the first law of radicals. Today we'll learn an important property for working with radicals that will help us simplify and manipulate expressions involving roots. The first law of radicals states that when we multiply radicals with the same index, we can simply multiply what's inside the radicals. Let's look at some examples to understand this concept better. Let's start with a simpler case to remind ourselves how exponents work. Consider 3 as a power of 2 times 5 to the power of 3. Using the properties of exponents, we can rewrite this as 2 times 5, all raised to the power of 3. This gives us 10 to the power of 3, which equals 1,000. Now, let's look at our second example involving fractional exponents. We have 2 raised to the power of 1/3, multiplied by 5 raised to the power of 1/3. Similar to our previous example, we can rewrite this as 2 times 5, all raised to the power of 1/3. This gives us 10 to the power of 1/3, which is the cube root of 10. Now, let's state the theorem formally. The product of radicals with the same index equals the radical of the product, if a and b are real numbers where the nth roots of a and b are defined. Then the nth root of a times the nth root of b equals the nth root of a times b. Let's now prove this theorem. We can rewrite our nth roots using fractional exponents. The nth root of a is equivalent to a raised to the power of 1 over n. Similarly, the nth root of b is b raised to the power of 1 over n. When we multiply these expressions, we get a to the power of 1 over n times b to the power of 1 over n. Using the properties of exponents, this equals the product a times b, all raised to the power of 1 over n. Finally, we can convert back to radical notation, giving us the nth root of a times b. Let's visualize this concept geometrically. For the square root case, when n equals 2, we can think of it in terms of areas. Let's say the square root of a represents the side length of a square with area a. Similarly, the square root of b represents the side length of another square with area b. When we multiply these side lengths, we get the side length of a rectangle with area a times b. The square root of a times b represents the side length of a square with the same area as our rectangle. This gives us a visual understanding of why the square root of a times the square root of b equals the square root of a times b. Now, let's apply this law to simplify some radical expressions. For example, let's simplify the square root of 16 multiplied by the square root of 9. Using the first law of radicals, this equals the square root of 16 times 9, which is the square root of 144, or 12. We can verify this by calculating each square root first. The square root of 16 is 4, and the square root of 9 is 3. 4 times 3 equals 12, which matches our answer. Let's try another example with cube roots. Let's simplify the cube root of 8 multiplied by the cube root of 27. Using the first law of radicals, this equals the cube root of 8 times 27, which is the cube root of 216, or 6. Again, we can verify this. The cube root of 8 is 2, and the cube root of 27 is 3. 2 times 3 equals 6, confirming our answer. It's important to note some key points when using this law. First, the radicals must have the same index for this law to apply. Second, this law works for all real numbers where the roots are defined. Finally, understanding this law makes simplifying complex radical expressions much easier. In summary, the first law of radicals states that when multiplying radicals with the same index, we can multiply what's inside and keep the same radical. Mathematically, this is expressed as the nth root of a times the nth root of b equals the nth root of a times b. This property is extremely useful when simplifying radical expressions and working with equations containing radicals. Try applying this principle in your own math problems to gain a deeper understanding. Let's begin by looking at some examples. Our first example has the values a equals 9 and b equals 4. For the first method, we calculate the square root of 9 times the square root of 4. The square root of 9 is 3, and the square root of 4 is 2, so we get 3 times 2, which equals 6. For the second method, we first multiply 9 times 4, which gives us 36. Then we take the square root of 36, which is 6. As we can see, both methods give us the same answer, 6. Let's look at another example. Here, we have a equals 25, and b equals 4. Using the first method, we calculate the square root of 25 times the square root of 4. The square root of 25 is 5, and the square root of 4 is 2, so we get 5 times 2, which equals 10. Using the second method, we first multiply 25 times 4, which gives us 100. Then we take the square root of 100, which is 10. Again, both methods give us the same answer, 10. Let's look at one more example. This time, a equals 1/4, and b equals 100. Using the first method, we calculate the square root of 1/4 times the square root of 100. The square root of 1/4 is 1/2, and the square root of 100 is 10, so we get 1/2 times 10, which equals 5. Using the second method, we first multiply 1/4 times 100, which gives us 25. Then we take the square root of 25, which is 5. Once again, both methods give us the same answer, 5. Now, let's look at a few more examples with different values. Thinking Phase Quick Challenge. Try to calculate these examples yourself before I show you the solutions. Here, we have it equals 16, and b equals 1/9. Using the first method, we take the square root of 16 times the square root of 1/9. The square root of 16 is 4, and the square root of 1/9 is 1/3. So, 4 times 1/3 equals 4/3. Using the second method, we first multiply 16 times 1/9, which gives us 16/9 or 4/3. Then we take the square root of 4/3, which is 4/3. White heavy check mark as expected. Both methods give us the same answer, 4/3. Let's do one final example. Here, a equals 4/49, and b equals 64. Light bulb tip: be careful with fractions in square roots. Always simplify when possible. Using the first method, we calculate the square root of 4/49 times the square root of 64. The square root of 4/49 is 2/7, and the square root of 64 is 8. So, 2/7 times 8 equals 16/7, or approximately 2.29. Using the second method, we first multiply 4/49 times 64, which gives us 256/49. Then we take the square root, which is 16/7, the same value we got with the first method. White heavy check mark correct. Both methods yield the same result, 16/7. Now, let's understand why these two methods are equivalent. The equivalence of these two methods is based on the properties of exponents and radicals. We know that the square root of a number is equivalent to raising that number to the power of 1/2. So, the square root of a times b can be written as a times b raised to the power of 1/2. Using the laws of exponents, we can rewrite this as a raised to the power of 1/2 times b raised to the power of 1/2, which is equivalent to the square root of a times the square root of b. This proves that the square root of a times b is equal to the square root of a times the square root of b. Calculate the product of the square root of 28 and the square root of 7. To solve this problem, we'll use the product rule for radicals. This rule states that the product of radicals with the same index equals the radical of the product of the radicands. In other words, the square root of a times the square root of b equals the square root of a times b. Next, let's multiply the numbers inside the square root. 28 times 7 equals 196. Now, we need to simplify this radical. We recognize that 196 equals 14 squared. The square root of a perfect square equals the base number. So the square root of 14 squared equals 14. Let's move on to our second example. Calculate the product of the square root of 6 and the square root of 8. Again, we'll apply the product rule for radicals. The square root of 6 times the square root of 8 equals the square root of 6 times 8. Now, let's multiply 6 times 8. 6 times 8 equals 48. For this problem, we don't have a perfect square yet, so we need to look for the largest perfect square that divides 48. We can factor 48 as 16 times 3, where 16 is a perfect square. Using the product property of radicals in reverse, we can write this as the square root of 16 times the square root of 3. The square root of 16 equals 4, so our expression becomes 4 times the square root of 3, which we write as 4 root 3. For our final example, let's calculate the product of the cube root of 3 and the cube root of 5. Just like with square roots, we can apply the product rule for cube roots. The cube root of a times the cube root of b equals the cube root of a times b. Let's multiply the numbers inside the cube root. 3 times 5 equals 15. The square root of 27 multiplied by the square root of 3. To solve this problem, we'll use the product rule for radicals. This rule states that the square root of a times the square root of b equals the square root of a times b. Using this rule, we can multiply what's under the radical signs. So, the square root of 27 multiplied by the square root of 3 equals the square root of 27 times 3. Now, let's calculate 27 times 3, which is 81. The square root of 81 is 9 squared, which equals 9. Let's move on to our second example. The square root of 0.2 multiplied by the square root of 0.18. Again, we'll use the product rule for radicals, but to make our work easier, let's convert these decimal numbers to fractions. 0.2 can be written as 2/10 or 1/5, and 0.18 can be written as 1800ths. We can simplify these fractions further. 2/10 is equivalent to 1/5, and 1800ths is equivalent to 9/50ths. Now, applying the product rule for radicals, we get the square root of 1/5 times 9/50ths. Multiplying these fractions, we get 9 over 250. We can simplify this further. 9 over 250 is equivalent to 9 over 250, which can be written as 9 over 250. To simplify further, we can express 9 as 3 squared and rewrite our expression. Now, we need to simplify the square root of 250. 250 can be expressed as 25 times 10, and 25 is 5 squared. Using the property of radicals, the square root of 5 squared times 10 equals 5 times the square root of 10. Simplifying further, we get 3 over 5 times the square root of 10, which can be rewritten as 3 over 5 times 1 over square root of 10. Let's multiply the cube root of 36 by the cube root of 6. For cube roots, the product rule also applies. The cube root of a times the cube root of b equals the cube root of a times b. Applying this rule, we get the cube root of 36 times 6. Multiplying 36 by 6, we get 216. Now, we need to find the cube root of 216. Note that 216 is 6 cubed, so the cube root is 6. We need to multiply the square root of 3 over 2 by the square root of 8 over 27. To solve this, we'll first apply the product rule for radicals. This rule states that the product of square roots equals the square root of the products. So the square root of a times the square root of b equals the square root of a times b. Next, we need to multiply the fractions inside the radical. When multiplying fractions, we multiply the numerators together and the denominators together. So 3 over 2 times 8 over 27 equals 3 times 8 over 2 times 27. Now, we can simplify this further. We notice that 4 over 9 is a perfect square because it equals 2/3 squared. When we have the square root of a perfect square, we can simplify by taking the square root, which gives us 2/3. Let's move on to our second example. Here we need to multiply the cube root of 0.01 by the cube root of 0.8. Similar to our first example, we'll start by applying the product rule for cube roots. The product rule states that the cube root of a times the cube root of b equals the cube root of a times b. This is true for any nth root, not just square roots. Now, we need to determine if 0.008 can be simplified. If we have a perfect cube under a cube root, we can extract it. In this case, 0.008 is equal to 0.2 cubed. So the cube root of 0.008 equals 0.2. For our final example, we'll multiply 3 root 2 by 2 root 3. This example involves coefficients outside the radicals. When multiplying expressions with coefficients and radicals, we multiply the coefficients together and the radicals together. So we have 3 times 2 for the coefficients and the square root of 2 times the square root of 3 for the radicals. We need to multiply -3 times square root of 5 and -2 times square root of 20. Let's write this as -3 square root of 5 times -2 square root of 20. To solve this problem, we'll break it down into steps. First, we'll multiply the coefficients. -3 times -2. Negative times negative gives us positive, so we get +6. Next, we need to multiply the radicals. To multiply square roots, we multiply what's inside the radical signs. So square root of 5 times square root of 20 equals square root of 5 times 20, which is square root of 100. Now we can simplify the square root. Square root of 100 equals 10, because 10 squared is 100. Finally, we multiply 6 times 10 to get our final answer, 60. Now, let's look at our second example. We need to multiply square root of 2 times square root of 18. Let's follow the same process. When we multiply square roots, we multiply what's inside the radical signs. So square root of 2 times square root of 18 equals square root of 2 times 18. Now we compute 2 times 18. 2 times 18 equals 36. So our expression becomes square root of 36. Finally, we simplify the square root. The square root of 36 is 6, because 6 squared is 36. So our final answer is 6. Let's try a more complex example. We need to multiply negative 5 times square root of 6 and negative 2 times square root of 18. First, let's separate and multiply the coefficients. Negative 5 times negative 2 equals positive 10. Next, we multiply the radicals. Square root of 6 times square root of 18 equals square root of 6 times 18, which is square root of 108. Now we need to simplify the square root of 108. To do this, we'll find the largest perfect square factor of 108. We can factor 108 as 36 times 3, where 36 is a perfect square. We know that square root of 36 equals 6. So our expression becomes 10 times 6 times square root of 3, which is 60 times square root of 3. Our final answer is 60 times square root of 3, or 60 square root of 3. Let's summarize what we learned about multiplying radical expressions. First, we multiply the coefficients outside the radicals. Next, we multiply the expressions inside the radicals. Then, we simplify the resulting radical by finding perfect square factors. Finally, we multiply any remaining numbers to get our final answer. With these steps, you can solve any radical multiplication problem. We need to compute the cube root of negative 2 multiplied by the cube root of 5. To solve this problem, we need to use the product rule for radicals. This rule states that when we have the same index for both radicals, we can multiply what's inside the radicals. So the cube root of a times the cube root of b equals the cube root of a times b. Let's apply this rule to our problem. We'll use the product rule with it equal to negative 2 and b equal to 5. So the cube root of negative 2 times the cube root of 5 equals the cube root of negative 2 times 5. This gives us the cube root of negative 10. So our final answer is the cube root of negative 10. This is our final answer because we cannot simplify the cube root of negative 10 any further. Now, let's move on to our second example. In this problem, we need to compute the square root of 14 times the square root of 7 times the square root of 2. Again, we'll use the product rule for radicals. Since all of these are square roots with the same index, we can multiply what's inside. Step 1. Let's combine all the square roots under one radical. The square root of 14 times the square root of 7 times the square root of 2 equals the square root of 14 times 7 times 2. Step 2. Now, let's multiply the numbers inside the radical. 14 times 7 is 98, and 98 times 2 is 196. So we have the square root of 196. Step 3. Finally, we need to find the square root of 196. We recognize that 196 is 14 squared. So the square root of 196 equals 14. So our final answer is 14. We've simplified our expression completely to a whole number. Let's summarize what we've learned. When multiplying radicals with the same index, we can combine them under one radical and multiply the values inside. This is known as the product rule for radicals. For example, we saw that the cube root of negative 2 times the cube root of 5 equals the cube root of negative 10. And we also saw that the square root of 14 times the square root of 7 times the square root of 2 equals 14. Remember to always check if your final radical can be simplified further. Practice these concepts with more examples to master the multiplication of radicals. Let's look at our example problem. We need to find the product of the cube root of 9 minus square root of 17 multiplied by the cube root of 9 plus square root of 17. Let's start solving this step by step. First, we'll apply the rule for multiplying expressions with the same radical index. When we multiply expressions with the same index, we can multiply what's inside the radicals and keep the same index. So, we'll rewrite this as the cube root of the product of what's inside each radical. We get the cube root of, open parentheses, 9 minus square root of 17, close parentheses, times, open parentheses, 9 plus square root of 17, close parentheses. Next, we'll apply the difference of squares formula. This formula states that a squared minus b squared equals a plus b times a minus b. In our case, we have 9 minus square root of 17 times 9 plus square root of 17. This is in the form of a minus b times a plus b, which equals a squared minus b squared. So we can simplify it to 9 squared minus the square root of 17 squared. Now, let's simplify what's inside the cube root. 9 squared is 81, and the square root of 17 squared is simply 17 because squaring and taking the square root cancel each other out. So we get the cube root of 81 minus 17. Let's continue by calculating 81 minus 17. We get the cube root of 64. Next, we'll rewrite 64 as a power. Since 64 is 4 cubed, we can write this as the cube root of 4 cubed. Finally, we can apply the rule that says the nth root of a to the nth power equals a. So the cube root of 4 cubed equals 4. And that's our final answer. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.